You've already looked at some volcanic rocks, the textural and compositional differences, and I want to show you a bit more about different eruptive materials and the deposits they form. So if we just look at a cartoon of a volcano and the different sorts of eruptive materials that come out, and also, as it so happens, the type of volcanic hazards that relate to them, we can see several in this image. Those include um, ash clouds with very small particles, very fine particles of volcanic rock that get blown into the air, into an eruption cloud. We see volcanic gases that are also erupting with ash. We see tephra. That tephra is a term that includes any material like volcanic bombs or blocks. It includes ash, it includes pumice, any of that material that is ejected into the air is tephra. We also see lava flows, so lava flows there. We see lahars, which are these volcanic mud flows that result when hot volcanic material is deposited, either erupts into rain or is deposited onto snow or onto glacial ice or some such, and that melts that and produces a thick cement-like flow of mud and rocks. We also see volcanic landslides. This is particularly notable for the Mount St. Helens eruption in 1980. And we see pyroclastic flows. So this cloud here is representing a pyroclastic flow, which you could compare to uh, a volcano, like a hot glowing avalanche of volcanic material. So it's a very fast moving flow of ash and tephra and other volcanic material that is forming a fast moving hot landslide, knocking down everything in its path. We also see a lava dome forming on this side. So lava domes being more viscous material that might get erupted in a volcano. So all of these processes, all of these kinds of eruptive materials and these deposits will result from different kinds of volcanoes. All right, we start with we'll be looking at basalts. So I'll start with a couple of different kinds of basalt flows. And these are two images of poihoi that are not very viscous. So they're a fluid kind of basalt. This is supposed to say less than 55% silica. You may be familiar with poihoi or a'a as Hawaiian terms or seen examples of those in Hawaii. Poihoi flows are similar to a'a. They're both basaltic, but these don't move quite as quickly. They actually advance more slowly than the a'a flows, but they are more fluid, and it's also called ropey lava. The a'a lava is also basalt. It forms fragmented, a jagged, discontinuous surface compared to the ropey basalt. You can see the ropey basalts down here. And again, this is supposed to say silica content less than 55%. But these are two kinds of basalt flows that you might run across. What you probably haven't seen, but you maybe wondered if you're in the field and seeing these two kinds of flows side by side, is why do you get poihoi or a'a? And the answer is that oftentimes it's common for a single basaltic flow to change the kind of flow as it moves downstream or downhill. and it changes from a pohohoi to an a'a over time. So the pohohoi and a'a surfaces are created from cooling, so the lava is crystallizing. And initially, the molten material is pretty fluid, and it's not breaking. It's just flowing in a more fluid-like fashion. And to break or rupture the partially solidified material, so the crust on the lava flow, the amount of energy that is pulling on that lava flow by gravity has to be greater than the value that keeps the surface of the crystallizing surface of that flow continuous. So this is essentially a function of how quickly a crack can be healed in that crystallizing surface when it's opened. So if it heals quickly, then it's going to stay a fluid flow. If more energy is available than that critical value where healing is allowed, the cracking or the rupturing can occur more quickly than the healing. And so you end up with this fragmented, jagged surface. And if a crack, as I said, if a crack does heal, then you get this continuous surface. So if it's not able to heal itself, then you end up with the beginnings of an a'a flow. So this has to do with the rate of the energy that's applied, that is the product of the stress that's applied to the crust and the rate of the deformation of the flowing lava. And ultimately, when that rupturing occurs, when you get this cracking, that's when the transition begins from pohohoi to a'a. A third type of basaltic lava is possible, and these are block lavas. And here's an example from it's actually called the Fantastic Lava Beds, and this is in the northern part of Lassen Volcanic National Park. And instead of pohohoi or a'a, you get blocks of basalt. And this is correct now. The block lavas are a little bit more silica rich than the basaltic rocks that form pohohoi and a'a flows. So these are a little more silica rich, a little greater than 55%, and that change in amount of silica changes the structures that you're getting out of these flows. I mentioned volcanic ash and volcanic gases. These are the two most voluminous products out of a volcano. And the gases that are erupting most commonly are water, carbon dioxide, nitrogen, and sulfur dioxide. The pyroclastic ejecta, or the tephra that I mentioned, those include the finest particles are the ash. That's followed by lapilli, these pea-size pieces of ejecta. Or if it's larger pieces, this is also lapilli down here, this gravelly look to that lapilli deposit. Or these bombs. All of these are different kinds of bombs. And you see they're quite a bit larger than lapilli. These are formed from partially molten lava that's ejected into the air. And so it looks streamlined or formed and crystallized and cooled as it was flowing through the air. These are Peles tears, which have a similar sort of texture to the volcanic bombs that I just showed you. These are quite a bit smaller. There's a dime for scale. But these are often associated with Peles hair that I'll show you in a moment. And these are small little droplets of volcanic material, molten volcanic material that's erupted. And because they're small, they cool, they quench very quickly, and they solidify into these little glassy droplets. And Peles hair, which are these fine fine, potentially very long streams of volcanic glass that's erupted in a sputtering volcano. And again, Peles, tears and Peles hair are terms that were developed in Hawaii. Ash may be deposited and consolidated into thick piles of tuff. And so a tuff is a rock that is comprised mostly of ash-sized particles. And in this case, this is the Bishop Tuff on the left-hand side. And this results from the Long Valley caldera in eastern California. In one eruption, laid down a very thick pile of ash that resulted in this tuff. And if you look more closely at some tuffs, this isn't the Bishop Tuff, but another example of tuff, where you see the fine-grained matrix are the ash-sized particles, and that there are other pieces in here. They might be pieces of pumice or pieces of rock, and that's also a kind of tuff, but it gets a slightly different name depending on what those particles are. Blocks can also be erupted from, these are also pyroclastic ejecta, but and blocks are also greater than 64 millimeters in size. And these are erupted as already solidified material that gets ejected out of the volcano. We see volcanic glasses, and I've shown you this before in obsidian and pumice. And as I said already, volcanic ash is the most common type, and we see here an eruptive cloud that includes the ash that is moving away from the volcano. And we also see pyroclastic flows, so those hot, fast-moving landslides coming down the slopes of the volcano at the same time. And that's Mayon in the Philippines. Pyroclastic flow, if it is deposited and consolidated, we call an ignimbrite. So that's a result in this. You see a variation from this coarser material to finer material that gets deposited as the ignimbrite flows downhill and is deposited on the slope. I mentioned a lahar before. These are these volcanic mud flows. And as I said, these are very thick, cement-like flows that can include pieces of rock, pieces of the terrain, but it's very thick because it has it's fluidized volcanic material and volcanic ash that makes it results from snow melt often or glacier melt, and so it's a rapid melt. There's a sudden melting process that takes place that creates a surge that moves downhill and takes with it all the debris in its path, but it's also very thick and cement-like because of those fine particles of ash that are in it.